Okay, let's start the stream for today. Right, so the plan for today is test time scaling diffusion models using optimal control. Okay, right. Before we go into test time scaling, let's talk a bit about the geometric interpretation of diffusion. Well, according to the geometric interpretation, we have a series of manifolds. Just going to draw some manifolds here and so on till we reach here. Right, let's annotate. Give me a sec while I annotate this so that I can explain. T minus 1. Come on, man. Fit in the same line. Seriously. I see what's happening. Yeah, that's good enough. It just needs to make sense. Doesn't have to be fancy. Let's call this M0. Now, think of a manifold as a collection of data points, okay, that are all satisfying, let's say, a particular property. So, in diffusion, we talk about how we go from random noise to complete denoise sample. Starting from there, if you take a look, at any given time step or denoising step, all the generations that you're doing will have the same level of noise in it, especially because think about it, if you take this equation, which is, consider the flow matching equation. I'm going to take medium size sample at t minus 1. Okay, this is not a function, it is just, I'm just using this notation to represent the value at t minus 1, or maybe no, at t, except at any given time step t, the noisy sample is given by noise into t plus noise into time step plus 1 minus t into x, which is your original sample. That means at x equals 0, you will only have x, and at time step, let's say 1, you will only have noise. Each of these manifolds represents the collection of samples at any given noise, at any given noisy step t. So let's zoom in a bit. Right, now every denoising step basically projects a point from one noisy manifold to the next denoised manifold. So you're basically doing manifold traversal as you do denoising until you reach the manifold at time step 0, which is your manifold of all the possible images that can be generated by your model. For simplicity, I'm calling them images, but we are in the latent space of the VAE right now. Now let's talk about test time scaling. The most common test time scaling approach so far for diffusion models has been best of n, which is, let's say, current test time scaling approach is best of n samples. What this basically means is you start with multiple noisy samples from random noise, and you keep traversing the diffusion manifolds until you completely finish denoising. And then once you have, let's say, 4 images, then you use a vision language model, something like a Gemini Flash or something, and ask it to rate the images based on aesthetic score, how they align with the prompt, and so on. And then you basically choose one of those n samples. I think it's okay, but it's still not a great way of doing what you call it. I don't think it's an efficient use of compute for scaling inference time compute. So we have another class of problems in another class of problems. We call them inverse problems. So inverse problems. What happens in inverse problems is you start with a measurement, let's say y, you know the and let's assume the original sample is capital Y. Okay, that is hard to see. Let's call it y dash then. Okay, so maybe we'll change it. Let's call this y dash. The original is y, and measuring function is f. Now what I mean by this is, when you can't measure the okay, let's frame it this way. The function y dash is the value of y dash, the measurement is just the measuring function applied on top of the original. How does this make sense? To give you a real world example, think MRI images, JPEG compression, etc. So what this basically means is, for example, for MRI images, I'm not sure, I think it's called the radon transform or something, but your y dash is basically the frequency domain signal. F is basically resonant frequency of the hydrogen nuclei, and your Y is the actual tissue structure. So basically what you're doing is using a measurement, using a different function and converting it into the domain that you wanted. So for a simpler example, think of JPEG compression as, let's say, y dash is the low quality image, y, let it be the original uncompressed image, and f is the compression function. Now these are just forward problems. Where does an inverse problem come into picture? Let's say you have inverse problem basically means get the original signal back from the measured signal with the knowledge or estimation of the measuring function. I'm pretty sure there's a better name for this. It's not supposed to be called measuring function. This is just my intuition. Okay. Why is it an inverse problem? Because you are basically doing an inverse of this equation here. So y dash equals f of y, then y equals f inverse of y dash, right? So now we know what an inverse problem is. How does this apply to optimal control? So there have been a couple of interesting research papers in this direction, which is basically using diffusion priors to solve inverse problems. The way this works basically is that, let's take an example of the measurement. You know the measurement sorry, you know that this measurement y dash lies on the manifold of all possible generations here. So let's label it. It's hard to see. Orange. Yeah, let's call that y dash. So now we have a measurement on the manifold y dash. Now the problem is, starting from a point on the outer manifold, here, how do you traverse this trajectory to make sure that you reach this point y dash? That means at every step you control in a way that optimizes the trajectory to reach this path. Let's say you follow some path, you want to reach your final point on the manifold y dash. That is the optimal control problem, which is basically optimal control. Now taking that, there are a couple of interesting papers, but I would suggest you check them out by yeah, this is one of the people that I follow for talking about inverse problems, and I consider him one of the pioneers of inverse problem solutions and using diffusion models for solving inverse problems. In fact, this geometric interpretation I found mainly through his papers. While I won't delve into one of his papers, there was a particular paper that actually wanted me to try this out for what do I call it, test time scaling. Consider this paper by liter out RB modulation. Let's close this. Annoying. How do I close this? Right. Well, the summary of the paper is pretty simple. They do okay, let's go through this once. Given a single reference image, RB modulation offers a plug and play solution for stylization and content style composition. So you have a reference style, you can use the reference style and generate whatever text to images that you want in the same style. So you can think of what they're doing similar to an inverse problem. You have the measurement of your style and you have a starting sample and a condition. You are traversing the manifold in a way that that matches the measured signal from your sample or from your measurement to the final original sample that you're trying to predict. And looking at it this way, here style is the param, here content is the parameter. And we'll see how they do it. Right. Stochastic optimal control with a terminal cost. This is what basically we're attempting. Our controller is going to guide our denoising process towards the desired direction. We'll talk about the terminal conditions for test time scaling and inference later once we start getting into the code. But for now, let's see. All this is okay. Personalized diffusion models. Personalization using optimal control. So they talk about how it has two features: stochastic optimal controller, attention feature aggregation. Let's first look at stochastic optimal controller. The reverse dynamics in diffusion models can be framed as stochastic optimal control problem, the quadratic terminal cost. For personalization using a reference style image, use a consistent style descriptor to extract style features. So your measurement is via using this model CSD, and this is your measured signal psi of x naught f, which gives you the style features from the image, which is our measured signal. And your terminal cost is basically psi x naught of f, which is your measured signal, minus, okay, let's simplify this equation. What does this basically do? It is basically saying style measured from the reference image, or yeah, let's call it a reference image, minus style of predicted x naught based on the current noisy sample. So if you remember, in diffusion models you can predict the final denoised image at any time step t. So take this, if you look at, okay, I'll show you the equation. So what happens is, at any given time step t, we estimate what x naught is going to look like, and we apply CSD on top of the estimated x naught, and that difference in style is going to be the cost that we incur. This cost is used as a signal to optimize the current noisy sample. We minimize, so at every step we are basically minimizing the cost. Let's go to the algorithm and I'll show you. Where is algorithm 2? Okay, I was actually planning to use this original costly algo for this, but I'll see if I can use the second algorithm that they've mentioned. But yeah, consider this. You have diffusion step T, reference prompt P, reference image Z0, style descriptor psi, and score network, which is our denoising model. Step size eta, optimization steps M. So you pick a random noise, Gaussian noise, and for each of the denoising steps, set the initial controller variable u equals 0, and these are the optimization steps. If you remove this, what will be left is with a normal denoising loop, of course not including this, but this is basically where the optimal control happens. These steps add the control, estimate the predicted final image using the current noise levels and the denoised image value, denoised on the predicted noise values, right? Predicted score function values, compute the cost associated with the current prediction and the measured signal, and update the control value. So in the next step, whatever control is being assigned, it gets updated with xt plus u. So you have a not in the next step. After m optimization steps, yeah, in the next step it is added to xt, and after you are done optimizing for m steps, you have the final optimal control prediction denoised time step, and then you do the normal denoising to predict the xt minus 1 value. This is a little different from what I remember. Instead of forcing x0 to be decided by the dynamics of the reverse STA as in algorithm 1, we allow it to be approximately faithful to the dynamics. This is implemented by adding a proximal penalty x0 star equals minimum of x0 x of f minus psi x0 plus lambda x0 minus x0 of u xtu. I have to see how that is calculated in the algo. Let's go to algorithm 2. So we have the same things: time steps T, reference image Z0, style descriptor psi, score network, step size eta, okay, optimization steps M, proximal strength lambda. This is the new variable, new hyperparameter. Output is still the same, initialization is still the same, controller r dimensional u, what is it initialized by? I need to look at the code for this, I guess. This is not supposed to be random, I believe. So it is just a r dimensional zeros, could be. So compute posterior mean x0 given xt equals xt equals, okay, predict the value of x0 at any given time step at any given noise value first, initialize optimization variable x0 equals 0, okay, interesting. For m equals 1 to m, do cost x0 of x0 equals psi z0 minus psi x0. Okay, x0 is all zeros, so this is basically 0, and plus lambda x naught minus. Okay, so we start with, we assume that the final image is all zeros. Then you calculate the cost associated with the difference in the styles, and you also account for, and you also decide how much you are willing to accommodate for the difference between the dummy x naught and the estimated x naught. So your optimization variable x naught equals x naught minus eta into the gradient of x naught with respect to x naught. Sorry, the gradient of the loss with respect to x naught. Okay, this does simplify because you are only updating x naught and you are leaving behind, you're not iterating through the entire loss variable. Sorry, not loss variable. You're not doing gradient descent on the whole latent across all time steps. So update optimization variable x naught, compute previous state xt minus 1 equals ddim x naught xt. Fair. So you're basically not using the actual values of the predicted x naught, but gradients are being calculated only for a dummy variable x naught. So this should be much smaller. Yeah. Step size, optimizing steps m. I want to see hyperparameter lambda being referenced. Different tunable hyperparameters. Style is pretty consistent. Step size 0. Step size 0.01. So this is something I'm concerned about. Basically, whatever prediction model that you are using expects clean images, and we don't actually have clean images at given points of at any given point of at all these denoising steps. And even though we project from a noisy manifold, we have an estimated x naught to the noisy. We try to estimate x naught from the current noisy step. I'm not very sure if reward models or let's say any other measurements that we take will be accurate because of the noisy images. So I think stable cascade works well here, but for us we'll have to take a look what can be done. For obtaining the final personalized latent using algo 1 and algo 2, we follow the decoding process as per the inference pipeline of the adopted generative model. Right. So how do we approach this for test time scaling is what I was thinking of. Here the terminal cost is basically calculated by using style as your reference, using a reference style. But consider a text to image generation problem where you have text, and using a model like clip or ciclip, you can get the feature vectors for both text and image, which basically lie in the same latent space. Your prompt adherence problem during inference is basically just making sure both the text vector and image vector are close together. So it will be more like you calculate. So your terminal cost is going to be, okay, let's go back to algo 1 for now. We'll see how we can simplify it later to algo 2. Right. So here, instead of CSD being the measurement, terminal cost calculation using CSD, what we can do is apply clip text features, clip text model on top of the prompt minus clip image model on top of the estimated x0. So you have two vectors that lie in the same feature space, and you can use that difference as a cost. This is something I'm still wondering if it will work, because I'm using two different models and I'm not sure if that will work well. And as far as aesthetics are concerned, we can just add an additional term for a reward model and optimize for either positive reward or negative reward. That is the main idea here, to be honest, and I'm still exploring it, but I assume it will be worth the test. Not sure if it will work or not, but I just want to see if it works. Right. Let's take a look at the RB modulation code. If I less than tau is the number of optimization steps, I believe. Okay, that is number of time steps. Number of iterations is actually the optimal control time steps. So this is your inner loop for I in range m, which is what you see. One second. Why does it look like my stream is stuck? Let me quickly check the stream is working or not. Right. Looks like we're all good. Anyway, so this is basically the number of iterations. This is for I in tau, is what basically what the whole thing is happening here. at least I hope so. No, not that. For in range 0 to time steps. Noise condition long. This is taking into account CFG. First, model predictions, model and diffuse optimal control. Z naught equals X naught clone detach. Requires grad patch optimization dot atom. I don't see it as being set to 0 though. Like I don't see algo 2 being applied here. I also don't see push forward being mentioned anywhere in the paper unless I have missed it. Push forward. Okay, that is something to check. Okay, that is something I need to look into in detail. What is push forward transformation? Okay, that is interesting. This needs to be studied in detail, but let's start with flux maybe. Yeah. So what I'll do is I have diffuse already installed. This is transformer flux. I need the pipeline flux. Pipelines flux. Pipeline flux. Now let's create a new file. TTS flux pi. Right. Let's get the weights first. TTS flux import flux pipeline. I think I forgot to install transformers. restart the kernel. Pipe equals my bad. I didn't make any changes yet. Pipelines, no typos. And okay, should be fine. Try now. Great. Pipe equals flux pipeline okay, lab for slabs flux dot. Hope I got the name right. Sorry. From pre-trained torch p type torch dot b float 16 and 2 CUDA. I'm running it on an A40, so I should have enough space. Okay, I need to import torch. Let's see. Flux 1 dot diff. I knew there was a typo somewhere. Okay, the model is downloading the weights. We'll have to start modifying the pipeline. Let's create the baseline. Count equals to the universe with the red nebula in the background. And the words Blackbeard written on the side of the ship. What is the word count of this thing? For now, at least, I want to .26. Okay, that's good enough. I want to let it fit in the clip max length, which is I think 77, so I don't have to worry about the clip space as well. Why is it the download so slow? Okay, still pretty fast. Okay, let's start modifying the algorithm then. What will we need? We'll need the hyperparameters. One is enable optimal control. Mm, would it be just easier getting the models out of the loop? Anyway, let's figure it out as we go. Enable optimal control is false. What else do we have? This is diffusers. RP modulation. Alright, before we get into actually applying the optimal control, I want to check something. Which is basically, if I have, let's say, noise at a time step, denoise sample at time step t, can I project it and get the image? So I'm going to have, what is it called, flow match Euler discrete scheduler. The denoising time step right. What this basically means is that I have x t minus 1 equals xt plus sigma next minus sigma. Where sigma is just t by 1000 or t by max time steps, I believe, minus sigma into your model output. So let's take a look at sigmas. Sigmas are basically from 1 to 1 by number of inference steps, and your time steps are okay. Now replace your retrieve time steps, else if sigmas is not known, set time step sigmas time step scheduler. Okay, I have to go to scheduler, right? Set time steps. So yeah, time steps are basically sigmas into self-load configured number of train time steps. So your sigmas are basically from 1 to 1 by max number of time steps, which is close to 0 but not exactly 0. And your time step is just going to be, sorry, sigmas are not that. Okay, sorry for the confusion. Let me go back. So right, sigmas, your sigmas are going to be from 1 to 0. 0 is open-ended. Your time steps are going to be from 1000 to open-ended 0, because usually max time steps during training is set to 1000 usually. Right. Okay, so now what I basically wanted to check, sigma next is going to be smaller numerically than sigma, and sigma next is going to be, let's check that as well. Step index plus 1, step index plus 1. Okay, makes sense. So assuming your denoising for number of steps equals, let's say 5, your sigmas are going to be 1, going to be linear 1 by, your last step is going to be 1 by 5, which is what, 0.2. So you'll have 1, 0.8, 0.6, 0.4 and 2 as your sigmas. Your time steps are going to be 1000, 800, 600, 400, 200. If I'm not wrong. Do we append 0 at the end? I think we should be. Time step second divided by 1000. Okay, because that's what the model expects. Okay, I always assumed we denoised close to 0, but I didn't realize we don't actually do that. We don't denoise till step 0. My bad. But anyway, that is not a big deal. That is not what I was looking for. Now what I'm basically saying is, at index I equals so for I in time steps, not in, for I in, let's say, range length of time steps, your sigma is going to be sigmas of I. So which is, let's say, something like 1. Your sigma next is going to be sigmas of I plus 1, which is 0.8. So your prediction x t minus 1 equals xt plus 1 minus sigma next 0.8 minus 1 into model prediction, or let's call it just model output as usual. But this is your time step 1000. So the previous time step. So rather than it being x of t minus 1, it should be probably predicting time step 800 equals x 1000, your original sample, your original time step, current time step 0.8 minus 1 into model output. That means I can predict x0 using the same formula for x 1000 plus zero minus 1 into model output, or more generally x naught is always going to be x into current time step plus minus t into model output. This is going to be my estimated x0. So I need to check, or at least know, how this is going to look like. Give me a sec, I'll be right back. Okay, I'm back now. I was wondering if there was a way to approximate this without having to get the model output. I don't want to mess with the I can mess with the internals, but I want to see if there's a cleaner way of doing this. Let's take the flow matching noising schedule. Xt equals noise into t plus 1 minus t into image. Using the same formula, t equals model prediction at t into t plus 1 minus t into image. I just replaced noise with the estimated model prediction. Is that correct though? xt minus let's see. I'm not sure if this derivation will make sense. One minus t into image equals xt minus model prediction at time step t into t. But the model doesn't predict the residual noise. What does model predict? Model predicts the velocity, not noise. So this equivalence is wrong. Model prediction equals x0 minus xt. That is also wrong, because that would mean I can directly, okay, no, model prediction is 1 by delta t into x0 minus xt. This makes more sense. This is actually where the derivation for this actually comes from. So delta t is basically your difference in the time steps. So delta t into model prediction and yeah, blah blah blah. So if model prediction, model output, if I want to replace model output with velocity, I can simply do x0 equals xt minus t into velocity. Velocity is going to be x0 minus xt, your final noise, or let's say noise. So yeah, I think I'm just running around in circles. It's easier to just get this value, which is a projection at a given time step. Let me come back to this. I'll stop here today for now, probably, because I need to go back and revise a couple of things to make sure I'm not making a mistake, and we will continue this in the next stream.